This video is a video about isotopes. Yesterday we had a discussion about the number of protons, neutrons, and electrons in an atom. And we learned that you can use the atomic number of an atom to determine the number of protons and the number of electrons in an atom. And we learned that when you look at the atomic number of an atom, that tells you the number of protons and the number of electrons. Okay, today what we're going to talk about is we're going to talk a little bit more about that atomic number, or the atomic mass, excuse me, that's on the bottom of the screen, or on the bottom of the box on the periodic table. The atomic mass is, as we talked about yesterday, the number of protons and the number of neutrons in the atom. Okay, and so just like what we talked about yesterday in terms of the neutrons and the protons added together make up the atomic mass of the element. And so when we talk about, for example, the element carbon that has an atomic mass of 12, we know that 12 of that mass is made up of 6 of the protons, and so carbon also has 6 neutrons as well. So today what we're going to talk about is we're going to talk about how those neutrons can sometimes change. Okay, and when the neutrons change in an element, what we create what's called an isotope of that element. Okay, and so an isotope of a specific element is different in its number of neutrons. So an isotope is nothing more than an atom that again has the same number of protons but a different number of neutrons. So an example here of that might be, which of the following represents a pair of isotopes? So again, when we're talking about isotopes, we're talking about the same element. So we know that the protons can't change, but then we're looking for a different number of neutrons. So right away, answer B is out. And the reason that it's out is because an element with 7 protons is nitrogen. An element with 8 protons is oxygen. So those cannot be isotopes. Isotopes, again, have to be the same element. Okay. Answer D is also automatically out because it has a different number of protons. We've got 26 protons versus 29 protons. Okay, so really our answer either has to be A or it has to be C, because at least in both of those answers, it is the same element both times. You've got 6 protons and 16 protons. Okay, what's different between the two is you'll notice that in answer A, you have 6 neutrons and 6 neutrons. Okay, we know that can't be isotopes. Okay, answer C has the 16 neutrons and the 17 neutrons. Okay, so therefore our correct answer must be C. So isotopes are elements that are the same element but have a different number of neutrons. So in example number 2 here, it says, what's the difference between what we call carbon-12, carbon-13, and carbon-14? Notice in this case that I didn't specifically write the atomic number down below the atomic mass because the atomic number is known when you know that it's carbon. It obviously has an atomic number of 6. So what's the difference between carbon 12, 13, and 14? Is it represents those 3 different isotopes of carbon. Carbon 12 is the most common naturally occurring isotope of carbon, and it has 6 protons and 6 neutrons. Again, remember that this number up here in the corner is the atomic mass. And so if it's carbon 12, that means the mass is 12, and therefore of the 6 protons, there's 6 left over that have to be the neutrons. Carbon 13, therefore, is carbon that again still has the 6 protons, but now has 7 neutrons. And carbon 14 is again 6 protons and has 8 neutrons. Okay, carbon 13 is a pretty important version of carbon simply because it does play a pretty important role in the lives of doing some what's called radiocarbon dating. Radiocarbon dating is what they use to determine how long ago things lived. For example, they use radiocarbon dating to determine the age of the Kennewick man, which he lived about 5,500 years ago. Now, what do isotopes have to do with the atomic masses on the periodic table? So a lot of times students wonder, why are those masses on the periodic table? Why aren't they whole numbers? Why isn't carbon just 12 when it's 12.011? Why isn't oxygen? Why don't they just round that up to 16 instead of 15.99994? Okay, if the atomic mass really just is the protons and the neutrons, why not? Why is it not just a whole number? Why is oxygen not 16? Okay, and again, this is where isotopes come into play. Okay, and the reason that isotopes are important is because not every atom of carbon is exactly the same. Most of the carbon that naturally exists in the world does have 6 protons and 6 neutrons. But there is a small amount of carbon-13 and carbon-14 that does naturally exist in the world. For example, chlorine, the example given here, of the chlorine atoms that naturally exist in the universe, about 75% of them have 18 neutrons, which again with the 17 protons would add up to a mass of 35. However, the other 25% of the chlorine atoms actually have a mass of 37, and so therefore they have 20 neutrons. So about 75% of the chlorine atoms that naturally exist have 18 neutrons, but about 25%, so about 1 out of every 4 chlorine atoms that again just naturally exist in our universe actually have 2 more neutrons. And so again, it has a mass of 37, what we call atomic mass units. So then the question comes up of, okay, which one do we put on the periodic table? Do we just put the most common one? Should we just put the mass as 35? If we do, that totally discounts the fact that the other 25% of the chlorine atoms have a mass of 37. And so what they do is that in order to come up with these numbers that they have on the periodic table, they come up with what's called the average atomic mass. Okay, and so what they do is they take the one isotope of chlorine that has a mass of 35, and then they use its percentage, and then they take the other isotope of chlorine and its percentage, the 25%, and what they do is they average them together. And so, for example, oxygen is almost 100% oxygen-16. However, there is a very, very, very small amount of oxygen-15 with only 7 neutrons instead of 8, right? That naturally exists. And so what happens in that case is when that very, very small amount of oxygen-15 that exists is averaged into the 99.9% of oxygen-16, and so that's why with oxygen you end up with that 15.9994 atomic mass, because again it's almost exclusively oxygen-16, but you have that very, very small amount of naturally occurring oxygen that does have a mass of 15 rather than 16. Okay, so what we can do is we can actually calculate this using an equation. So mathematically we can calculate again the average atomic mass based on what's called the percent abundance. Okay, again, the percent abundance is that number right up here, is that naturally occurring chlorine is about 75% chlorine-35 and about 25% chlorine-37. So the percent abundance is what percent of that element is naturally found in nature. Okay, and the way that we do that, so to calculate the average atomic mass of an element, we take its percent abundance. So we'll have to be given some data. They'll give us some data about one of the isotopes of an element, and then another isotope, and maybe another isotope. And so what we do is we take the percent abundance of that one isotope and we multiply it by its atomic mass. Okay, so let's say again, let's use that chlorine as an example. Chlorine is 75% chlorine-35. So we could just take 75 times 35. So I have just done this first part right here, the percent abundance times its atomic mass. And then we can see the next part is we add. Okay, so then we go plus, the next percent abundance is 25% for chlorine. And again, these are kind of averages. These are not the exact amounts. And the atomic mass of that isotope is 37. And when you take those two, and now notice there's a plus sign here and then dot, 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 which means if there's 3 isotopes, then you throw the other one in there. So if this is like 70% and 20%, then the next one would be 10%. And as you, depending on how many isotopes there are, you can have up to 3, 4, 5, maybe even 6 of these in your equation. Okay, and when you average those out, and then again you divide by 100, you find that the average atomic mass of chlorine is again very close to 35.5 on the period, the number you see on the periodic table. Okay, so here's another example of that. Example 3 says the percentage of naturally occurring magnesium is the following. 69.5% of magnesium is magnesium 24. And 30.5% is magnesium 25. What is the average atomic mass of magnesium? Now I realize at this point you could stop. You don't have to do any of this right here. You can simply look at the periodic table, right? Look at the periodic table. What's the average atomic mass of magnesium? Well, it's 24.305. Okay, but I'm just trying to show you how do they come up with these numbers? Where did this number 24.305 come from? Again, we take the atomic mass and we multiply it by its percent. So the atomic mass is 24 and we multiply it by 69.5. Okay, so that's our first step. And then we add it to the other atomic mass and its percent. So 25 times 30.5. And then we again multiply, add the two numbers together, then divide by 100. And you get an answer of 24.305 atomic mass units. Okay, so example 4. So it says silicon has 3 naturally occurring isotopes. So we can see that silicon 28, even though that rounded has a mass of 28, it actually has a mass of 27.98. And its percent abundance is 92%. Again, that means that most of the silicon that exists is silicon 28. But then there's also silicon 29 that has a percent abundance of just under 5%. And silicon 30 has a percent abundance of just over 3%. So part A, which of the 3 isotopes is most commonly found in nature? Absolutely silicon 28. Okay, now why is it silicon 28? Because of that number right there. Over 90% of it is silicon 28. Okay, and then part B, what is the average atomic mass of silicon? Okay, so in this case, again, we could stop right now. We could look at the answer on the periodic table, and we could determine what its average atomic mass is without doing any math at all. But let's make sure we actually know how to do this. So to solve this, we're going to take the first mass, which is, and again, well, what if they give us 2 masses? Which one do I use? This is the real mass. This is the rounded mass. What's the better one to use? Of course, the real mass. So we're going to take 27.98 and we're going to multiply that by 92.23 plus the next one has a mass of 28.98 and we're going to multiply that by 4.68 plus, and now the last one, 29.97 times its percent, 3.09, and we're going to divide that all by 100. So unfortunately, I do not have my calculator with me. So let's go ahead and pull up the calculator here. On a computer, your calculator would probably be better to use here. So I'm going to take 27.98 times 92.23. Get that answer. Plus 28.98 times 4.68 equals, and then plus, oh, is this calculator not using the, oh, I should have used parentheses, darn it. Well, let's see if it works out or not. Plus 29.97 times, oh, see, I see it added it first, even though it's supposed to multiply. 3.09 equals a crazy number, so that is not correct. So if we just pull up the average molar mass of silicon from the periodic table, we can see that it's a number that's just slightly over 28. So let's see if we go on Google, we can see that. Average atomic mass of silicon is, yeah, 28.0855. Okay? And that's what we would get there with that answer, 28.0855. Alrighty. So when you're calculating the average atomic mass, as you can see, it is the mass of each of those individual isotopes. So how many naturally occurring isotopes does silicon have in nature? Well, we can see there's 3 of them. And again, those 3 add up to 100%. So isotopes, again, just a quick summary here. Isotopes occur when you have the same element with a different number of neutrons. And the reason that isotopes are important is because many of them naturally occur in nature. And so in order to come up with an atomic mass on the periodic table, we use the average of those different isotopes. And we use this equation here to determine the average atomic mass of an element. And we can use that to identify. So sometimes they won't even tell you what element it is they'll say, identify the following element. And what you'll do is you'll get an average atomic mass, and once you have that, you can then look at the periodic table and see which element has that average atomic mass, and you'll be able to identify it.